Hi there. Today I want to talk about machine learning and artificial intelligence, and in particular with the rapidly changing state of the art, what is easy, what's medium, and what's really hard today with machine learning and artificial intelligence, what is likely to change in the future, where were we just a few years ago. So that's what I'm going to talk about today. Okay, so machine learning, easy, medium, and hard. Now, across nearly every discipline, both in terms of scientific research, industry, and in our everyday lives, machine learning is redefining the art of what is possible. And even what we thought was possible 5 years ago is getting redefined now with tremendous advances. Okay, so these are driven by rapidly increasing volumes of data. So for example, Google Images is this vast amount of data on naturalistic images. The Facebook database is a tremendous database of millions and millions of human faces from different angles and different perspectives. You have surveillance cameras, Google searches. So the amount of data is growing at an incredible rate. In addition, you have faster and faster computers, parallel architectures like GPUs, better data storage, so cheaper hard drives and memory and faster transfer. And so you have this kind of culmination of big volumes of data and hardware that can handle those big volumes of data. And in the middle, you have advancing and emerging mathematical techniques, kind of applied math, statistics, being developed in many different disciplines. These algorithms are essentially mining features from this big data and allowing you to essentially pull out relevant information, coherent patterns, and actionable information. And so these kind of three things together, so big data, big computers, and better, sharper tools, algorithms, are really driving this field forward at an incredible rate. Okay, so that's what we're going to talk about, and this is going to be just through a couple of case studies. So what is actually possible in examples. And I really like this XKCD comic, so I'm going to put links to as much of this as possible so you can go find these links and dig in. This is an XKCD comic I really like, so I'll let you read it for a minute. So I think this is kind of fun because it really is easy in the modern era to think of machine learning as almost like a magic wand, okay? So, or a black box, right? You put in data, you get out awesome predictions and results, or you hire someone and you say, okay, I want machine learning to solve all my problems, go. And so really it's easy to set up problems that are trivial with data science. So telling if a picture is taken in a national park is just a matter, photos are tagged with location, but figuring out if the photo has a bird in it, much, much harder, right? You need a research team in 5 years. Now it's funny, this comic is from a number of years ago when this was actually hard. Now with the incredible pace of progress in image classification, this is basically a solved task by many research teams across the world. Okay, so this also illustrates that what used to be very hard and need a research team in 5 years, what used to be very hard is now essentially trivial. Okay. So facial recognition is a huge one. What I always tell my students is, and my collaborators, if you can take your data and make it look like an image, then you get decades of incredible research and algorithms for free, because image recognition, face recognition has been one of the cornerstones of machine learning, machine vision for decades. And a lot of the most powerful algorithms are developed for mining and classifying and making decisions based on images. So here you see a selfie. I think this was a picture that Ellen took with a bunch of celebrities, and some researchers essentially used the Viola Jones facial detector algorithm to automatically pull out all of the regions in the image that it thought were faces, and then you can use a face detector algorithm to tell who these faces are with pretty high accuracy. Okay, so for example, I think the Facebook facial recognition algorithm of who is who, so not just putting boxes around faces, but telling telling the user who the people actually are, is now approaching human accuracy in terms of classification, which is quite impressive, right? This has taken decades for algorithms to get as good as humans at telling who belongs to what face, but now they're able to do it. And fun fact, one of the ways that they actually do this, that image recognition and facial recognition algorithms actually do this and reach that human level performance. So for a long time, they were stuck a few percentage points below humans in accuracy. And essentially what bridged this gap, or at least one of the technologies, was estimating what is the actual skeletal structure, what's the three-dimensional structure of the face from this 2D image. So as a human, I have all of this experience walking around the world in 3 dimensions and seeing people from different perspectives. So it's very easy for me to estimate the depth of a cheek or a nose, or how deep, someone's eyes are behind their, their forehead. And so that's the kind of technology now computers from these 2D images are able to estimate that skeletal reconstruction, and then that gives them enough information for that human level performance. Okay, so this is a problem people have been working on for decades now. I mean, I don't want to say it's completely solved, but everyone holds up their phone, and there's a number of people. Your phone automatically puts boxes around all those people's faces. So that's using very similar technology, which is very likely based on the Viola-Jones algorithm. Okay. So a lot of image recognition, so image classification used to be a kind of a grand challenge machine learning and machine vision problem. And then I think in 2012, this landmark data set, this ImageNet data set, was curated and put online for all of the world to try to develop and test their machine learning algorithms to classify different images. So this is just a tiny, tiny slice of these millions and millions of images that were labeled. Okay, so these are labeled images where you know what is actually in the image. So if I zoom in on a little region here, you can see there's everything. Okay, there's a picture of an iPod and a person with some headband, and there's every picture you could imagine, and they're all labeled. And so this massive volume of training data, along with the massive increase in computer power and GPUs and deep neural nets, made this kind of quantum leap in performance of image classification. So this was the landmark data set and also demonstration of deep learning where it really got back on the map. So people have been using neural networks for decades, but having this wealth of labeled data, so this is called supervised classification when you have labeled data, so someone's telling you what is what, and then you're learning that. And that was really kind of this massive change in the performance of deep learning that really started it off on this exponential trajectory. And it's undeniable that deep learning has essentially improved almost every field it's been applied to where there is this kind of wealth of data, of labeled data. So it's really changing what's possible in terms of performance metrics in many, many tasks. Now the caveat is you need a tremendous amount of training data. So lots of times we want to learn with minimal amounts of data. That's still quite hard. Humans and biological systems are experts at one-shot or two-shot learning, where you have a few trials of information and you can adaptively learn that very quickly because you have this experiential framework to hang that information. But computers are getting better when you have tremendous volumes of data. So this used to be kind of a grand challenge, hard problem. Now this is kind of the base level, entry level. So now this is kind of an easy problem because we have big enough computers and big enough data sets. So image classification is doable now. This is just kind of an example of how rich this ImageNet data set is. So nearly everything you can think of. So these are like tractor, trailer, or sorry, these are harvesters, right? Like John Deere trucks. These are pictures of broccoli. These are some purple flowers. Pretty much anything you can think of. There are dozens, if not hundreds, of examples of these images in this ImageNet training set. And so to some extent, anything you will see in the future, you are likely to have seen something similar to it in this training data. So that's also one of the catches with this deep learning is oftentimes we think of it as like a really fancy interpolation, but you have enough richness of the training data that anything in the future you'll see can kind of be interpolated based on what you've seen in the past. And it's this nonlinear hierarchical interpolation. Now, this is an interesting, I'm pulling this picture from this great paper in CVPR 2017. I encourage you to go read it. The first time that I downloaded and used this image, I didn't even realize this second column here, or maybe this fourth column, these are actually artificially generated images by the deep learning algorithm. So these are called GANs, generative adversarial networks, where essentially you have one part of the network that's trying to tell, is this a real image of a purple flower? Is this a real image of a harvester? And then you have another network which is kind of trying to generate images to trick your classifier into thinking that it generated a purple flower or a tractor. So they're kind of adversarially training against each other. You have a classifier, kind of the traditional ImageNet classifier, and then you have this generative network that's trying to trick it. And so remarkably, I mean, if you look very closely, you can see that these are kind of just make-believe images. This isn't really broccoli. This is just green blobs in a statistical pattern that looks a heck of a lot like broccoli from where I'm standing. And similarly with these harvesters. So what's really, really interesting is now actually generating fake images that can trick a trained classifier. This totally fooled me the first several times. That's how good these fake broccoli images are. They look just like broccoli. These purple flowers are even better. And so these GANs are getting amazing at kind of faking these naturalistic images, and they're even getting to the point where you can fake videos. So this is becoming a big kind of social hot topic right now, because what if I can fake a video of a world leader saying something either offensive about another country or, you know, saber rattling? Like, what if I can actually fake a video of a politician and trick another country into thinking that it was really our leader or another country's leader? So there's this kind of misinformation potential when you can fake images and fake videos that's really quite worrisome. And it's progressing at a rate that we kind of, I don't think anybody saw this coming, how fast we were going to be able to fake videos. I mean, this is science fiction technology that's now pretty much possible if you have enough training data. Okay, so very interesting topic. Now, image classification is not, I don't want to make it sound like it's completely done. There are still things that humans are able to do that machines really aren't, because we have intuition. So I love showing this picture, blueberry muffin or chihuahua. Okay, so this is kind of a comical example of where a computer fails. So a lot of these chihuahuas really do look a lot like a blueberry muffin. I mean, this one just tricked me a little bit. But a trained human looking at this knows for a fact which ones are chihuahuas and which ones are blueberry muffins. We just have this kind of deeper intuition, this almost physical intuition of what is what. And that's really more subtle than what computers have. Okay, so I also like fried chicken dog. I think that's one of my favorites. You know, is it a dog or a fried chicken? Okay, so, and there's tons of examples like this where you can trick machine learning classifiers with pretty simple and obvious misclassifications. But overall, image classification is pretty good. And so what people are moving towards now is more rich scene classification of movies, kind of real-time surveillance of many, many images at many scales. So can I, in real time from a surveillance video, can I track all of the cars, pull out their license plates? Can I detect erratic behavior? And what is erratic behavior? Well, that's hard to quantify. There are outlier events. Let's say, I had the London underground metro platform, and everybody rushes in and crosses paths and goes their separate ways. Can I tell if someone left a piece of luggage by a support pillar? Okay, that's a very important surveillance problem. Very unstructured, very hard. So can you detect something that's out of the ordinary, that's abnormal, something that you should focus your attention on and get a human to look at? Okay, so that's becoming the new kind of difficult level of machine vision problem. Creating and analyzing and classifying movies is a very hard problem. So I think that the YouTube database is going to be kind of that next ImageNet database. Now we have, I don't know, millions or billions of hours of video content. And that's an even vaster data set that we really don't have the computational power to do the full analysis on. So that's kind of where we're going to have to catch up to in terms of computational power. And this is extremely important for self-driving cars, for autonomous platforms, for drone surveillance. You know, Amazon Prime Air is going to be flying around drones. They need to be understanding the scene that they're working in. Self-driving cars are going to be driving around. They need to understand what's happening in their environment. Okay, so this is, I don't know, kind of medium hard. We think it's doable, but it's not done yet. Image captioning is one of my favorite examples. So this is really neat. This is, again, one of those problems that even a few years ago we would have thought, like, a computer, sure, they can classify an image like dog, cat, blueberry muffin, but actually making a coherent sentence describing what they see in a scene, that seemed like a very hard task maybe 5 years ago. Okay, and so it's kind of remarkable how far image captioning has come. This is a great paper I recommend you reading, another CVPR from 2015. And you can see in these images it does a pretty good job. Man in black shirt playing guitar, construction worker in orange safety vest working on road, 2 young girls playing with Lego toy. Well, I'm not sure she's a young girl or not, but you know, it gets the gist of the picture. There's a kid playing with Legos. Okay? And it's actually quite good. You can read about the statistics of how effectively they can and can't label these scenes, and it's really quite remarkable. Now, there's some comical examples of when it fails. So, young boy holding a baseball bat, you know, it's clearly not. Cat sitting on a couch looks more like a ferret to me. And this is my favorite, a horse standing in the middle of the road. So, no horse, but there is a road. Okay, so it's much better than we thought it would be just 5 years ago, but still not perfect. Okay. So that's kind of image classification and scene classification. And I think I'm going to go back here for a minute. So one of the points I like to make when I talk about image captioning and classification and surveillance is, where do we think this is going? Do we think that the machine is going to get better at classifying scenes? Are they going to be able to watch a movie, you know, Iron Man, and are they going to be able to write a transcript? Are they going to be able to write essentially the script of the movie just by watching all of those scenes evolving in time? That's something that we can't do now with machines, but we're working towards that. And so you have to ask yourself this question when you're thinking about easy, medium, and hard. Also, what is possible, and how feasible is it that this will happen in the near or long future? Okay, and so one of the kind of baseline questions I ask myself is, can an average human do this task? Okay, so an average human, yes, they can image classify, they can more or less watch a scene and see, kind of track a car or see if something suspicious happens. An average person can caption an image pretty accurately. And so these are all examples of something that don't require extremely specialized, you know, a lifetime of skills kind of knowledge to do. And so these are things we think computers can probably do if they have enough training data and we have powerful enough computers and we try to tackle it long enough. You should also ask yourself the question, are there $100 billion companies that care about this problem? And for this one, absolutely. So that's another thing that will, you know, be driving progress in these fields is it actually impactful and important? Is it something that is worth doing, and is it worth spending real resources and human lives working to solve these problems? And so, you know, image captioning, surveillance, absolutely. Now, there are some tasks where it does take a long time for humans to build their expert intuition, but we actually can train machines to do it if you have enough training data. So I think there are some interesting examples of medical imaging where it takes trained humans long times to figure out what they're looking at in these images. But with that labeled images, you can essentially transfer that human experience into machine classifiers. But then making real actionable decisions about how to help a patient improve their health, that's something that's going to take a lot longer for machines to do well. Or at least we think now. Maybe in 5 years, we'll just be blown away with the performance. Okay, so I'm going to switch gears a little bit. Now we're going to talk about actually wrapping this machine learning. So what we've done so far is just the algorithm is kind of this brain in a vat, or this, it's just watching the world and classifying and annotating and labeling things. So it's kind of not touching the world, it's just observing and classifying. Now what I'm going to talk about is actual control. Okay, so I love control theory. I think, if you're going to model a system, if you're going to build a model, you should be trying to change the system somehow, or oftentimes we're trying to change the system. So for example, Amazon is collecting this data and understanding how humans decide to buy things and our preferences. But eventually, I think they want us to buy more stuff, and they want us to be happier when we buy it. And to, they're essentially trying to manipulate the system so that everybody benefits. That's how this should hopefully work. And so, kind of changing the behavior of the system. So in a self-driving car, you're not just scene classifying, you're moving through this world. If I have a robot walking, I'm not just classifying objects, I'm actually interacting with the world. So this is another one of those kind of amazing topics that deep learning has been taking off. So this is a 2013 NIPS paper playing Atari with deep reinforcement learning. So reinforcement learning is a type of kind of data-driven experiential control where you try things, you see what happens, you build some estimate of the value of different actions at different times. And basically people are using the wealth of data and deep learning to augment this reinforcement learning for dramatically improved performance. So this is a classic Atari game. I think it's called Breakout. And basically, it's kind of like Pong. You're moving this thing back and forth, trying to bounce this little red dot, and you're trying to break this rainbow. You're trying to get all of these rainbow blocks broken. Okay, so this is kind of a challenging game. After 2 hours of playing this game, and all it has is the pixels on the screen, and it knows what its score is. After 2 hours of playing this game, it's pretty good. Like, I don't think I could play this effectively, maybe with 2 hours, but I don't think so. This is pretty good. But the deep learning, what you really want, what the ultimate goal in this deep reinforcement learning is the machine not just being good, but learning these kind of magic transitions where it goes from being good to learning the trick, the kind of the secret of the game, okay? So the cheat, okay? And here you're gonna see after a couple more hours, it learns the strategy that is much more effective for winning. Do you see this? Okay, so it broke through here, and essentially it just uses the physics of the game to break all of the blocks at once. Okay, so that's the promise of this deep reinforcement learning, is if you interact with the system enough, can you actually learn the rules, the physics, so that you can find these deep exploitations that are not just you playing the game well, but you being really a master. Okay, and we've seen, DeepMind, Google DeepMind, is not just playing Atari games, they're playing chess, they're playing Go, and they're beating the best humans in the world. They're beating hundreds of years of collected human knowledge and transferred knowledge now, essentially by playing and learning and adapting their strategy and finding these deep kind of exploitations and physics and symmetries of these structured games. And that's really, really exciting. So this is one of the more exciting areas of machine learning research, is kind of deep reinforcement learning. Okay. Another one I love, this is some great work in ICRA 2009. So again, please read this paper. This is kind of robotic reinforcement learning, okay? So imitation learning. So a human shows it how to do it a few times, maybe once or twice. You can read how many times. And essentially this machine, it has a white background, so I'm assuming it's using video data to figure out where the position of the blue cup and the red ball are. And after something like 15 trials, it's doing pretty good. I mean, like, it's getting as close as I would after 15 trials, probably. And after, a few dozen trials, it's basically learning the physics, it's refining its control strategy, and it's using this kind of data-driven policy here. So this is really important, this imitation learning, this kind of reinforcement learning from data, it's using computer vision to do this, is really important for a number of applications, especially things like manufacturing. This is super important. So I saw a talk by someone who works on this, and they said that, I think the anecdote was, they had one of their relatives, a kid, maybe a 12-year-old or something, try this game. And it took the child about the same number of trials to learn how to do this. Maybe a few less. Maybe they did it in 50 trials instead of 100, but the same order of magnitude learning rates here with this robotic arm and with a human child. So it's really remarkable. If you think about automation and manufacturing, you have this kind of forward assembly line model where the same machine is doing the same task over and over and over. I'm gonna turn this bolt, turn this bolt, turn this bolt. That's all that machine does. It was built to do that forever. But in modern manufacturing, maybe I have more customizable designs. Maybe I have a robot that has to do multiple different tasks in one area. It has a work zone. This is more like a skilled worker. And so you want to be able to teach those robots how to do new tasks quickly and how to transfer knowledge between one task and another. So this is very exciting. Another area that's driving tremendous research is robotics and also self-driving cars. So this is kind of a DARPA competition, and DARPA both has been pushing self-driving cars, but also robots. And this is just kind of a funny video of how bad a lot of these robot walking and manipulation tasks are. So we like to see videos of things like the Big Dog. Go Google Boston Dynamics Big Dog, and you'll see how great our robotics is now. But there are, for every success story of robotic walking or running, there's a lot of failure. These things don't have physics intuition yet. They don't have kind of our degree of control, authority, and actuation. And that's something I think is super important to think about. It may very well be, if you think of the science fiction future of 20, 30, 40 years from now, it may very well be that machines surpass our ability to pull out patterns and actionable decisions and reason based on data in many, many cases, in high-dimensional data. But robotic bodies are not nearly as good as biological bodies. So the fact that I have very sensitive sensation in my skin, I can feel very minute pressures and frictions and temperature changes. I can feel wind. I have, I don't know how many, but a ton of different muscle groups that can work in concert. I don't just have one servo joint, okay? And so the fact that you have this, this deep complexity of sensing and actuation in biological systems means that I can go out into the world and gather experience. I can be curious. I can try things. Think about when you were a kid and you had something like the ball in the cup. You would just play around with it for hours and you'd learn physics, and you'd also learn your own neural motor control systems and sensing systems. And so robotic systems are really far away in that sense. They don't have a body to carry them through the world to learn. Okay. So again, I want to change gears a little bit now. So we talked about what we think is going to be possible. What used to be hard is now easy in many cases. What's medium hard now we think will be solved in the future. And I want to point out a couple of cases that I'm going to go, so it's a little risky making a video in a field that changes so fast like this, but I'm going to go on and speculate that machine learning is not going to write the next great American novel anytime soon. It'll be classifying and writing captions of scenes better than we can, maybe, but it's not going to write the next great American novel. Because that requires not only a lifetime of experience, but it requires a singular kind of insight and set of experiences and giftedness that is very rare. It can't be replicated. These are far, far outlier events of genius and human skill and intuition. I don't think we're going to get this anytime soon. So it does beg the question, can you generate other types of fiction, maybe not the next great American novel? And there was this really cool example by Botnik Studios. I love this one. They used machine learning. They basically dumped all of Harry Potter into this learning algorithm, and they tried to generate their own Harry Potter fan fiction. And it's pretty terrible. I mean, no dig against them. It's impressive how good it is, considering that I would have never thought it could even get close. I mean, it has complete sentences, and some of the sentences are actually pretty interesting and pretty, they have a little texture, they have the right kind of words and feel. Other sentences are just ridiculous. And so I think we're pretty far away from this kind of generative fiction or generative paragraphs, but people are trying this now, and it's pretty interesting what people are able to do. In a more kind of serious vein, people, this was a while back, I guess 2015, a bunch of, some researchers at MIT essentially used machine learning to generate papers, academic papers. So, research papers for academic publication, and they actually faked and got a lot of these accepted. So basically, the scientific peer-reviewed publishing system was pretty embarrassing at letting through these fake papers that were just generated kind of by an algorithm, okay? And so I encourage you to read about this. So this is similar to that kind of fake news and fake videos and fake images. You can generate things that pass at least kind of the preliminary BS detector of professionals in the field, and that's worrisome. Maybe it says more about how little time we spend actually reading papers for review, but I think it's an interesting case study, okay? And then I also want us to be thinking about what is canonically challenging and what are things that machine learning probably can't solve, or at least can't completely nail. There will be fundamental learning limits for some systems. I think weather prediction is a really interesting one. So weather prediction, there's no doubt that machine learning and artificial intelligence can and will and is improving our prediction capabilities for dynamical systems like weather and climate. But there are hard information limits. This is a chaotic dynamical system, right? So everyone's heard of the butterfly effect. A butterfly flaps its wings in Texas, and it causes a tsunami somewhere else in the world a month later. And that's kind of ridiculous. I don't think anyone really, that's just a soundbite. But there are these sensitive dependencies on initial conditions that do occur in these complex, chaotic dynamical systems. So, and what that means is if I don't measure my system perfectly, if there is like 1% error in my measurements here, my future prediction a month from now, there might be a fundamental information limit based on that uncertainty now, amplifying through this dynamical system. I might not be able to tell where that hurricane is going to land a month from now, or if it's even going to form. So there are these information theoretic limits for these chaotic, uncertain, nonlinear dynamical systems, and that's going to be very hard for machine learning to really move the needle. So we actually need better measurements. We have hard mathematical theory that says for some prediction problems, you just need better measurements. You need more precise measurements at a finer grid scale, and then machine learning could definitely help with the modeling. Okay, so the last slide I want to show you is kind of this example, just what could go wrong. So I've shown you all of these great kind of science fiction examples of robots and self-driving cars. The computer's going to label scenes in movies and all of this really cool technology. There are some kind of worrisome parts of this all, right? So we should definitely be thinking, what are the implications of societal surveillance? Like when surveillance becomes cheap and easy, when my phone can just listen to everything I say and parse it into text and then make decisions based on that. When we have video surveillance watching everything, how is that going to change the world? Is it going to be a better place? Obviously, there will be some good things about it, but there will be some bad things. This is what all technology is like. This is just a very kind of digestible example of this, right? So in an Amazon cart, I buy a calculus book. It maybe suggests, hey, you might want a differential equations book or a physics textbook, right? Calculus-based physics. So it suggests what goes also with those objects. There have been cases where people have wanted to buy one good, and the learning algorithm, this is based on data, this is based on historical patterns of shoppers, presumably. It has suggested the parts to make dangerous devices, like this looks like we're making thermite, okay? So that's pretty worrisome that I go and I want to buy art materials and this algorithm is telling me, hey, maybe you should make thermite, okay? This isn't like this was a malicious algorithm or someone was trying to be destructive, but algorithms are only as good as the data you're training on, the historical data. And that's pretty worrisome that the historical data is saying, hey, make dangerous devices. This is also a huge issue if you are using machine learning for something like hiring people. If your corporation has historically made hiring decisions that are biased, then you don't want to train your algorithm on who are the best people to train, because you might get this biased workforce in the future also. This is also an issue with machine learning for who to give parole to, or how to set bail, right? So these are actual case studies people are doing right now. Is, can we use machine learning to help take some of the burden off of overburdened judges for setting bail, for parole, for things like that? But if you have a historically biased set of training data, if one segment of the population has been getting a biased treatment, if it hasn't been historically fair, you have to be very careful using that data for future inference and model building, or else you run the risk of baking that bias into the structure of your learning. And so blindly trusting the output of these algorithms, basing these on historical data, there's huge ethical and societal issues that we have to understand. So that's hard. Okay, so easy, medium, and hard. I really think that's one of the hardest issues we face. Okay, so that's basically it. I just kind of wanted to give you this high-level, kind of fun overview of what is currently easy, medium, and hard. What is hard now, maybe easy in the future, and vice versa. But really, machine learning and artificial intelligence, it's undeniable. This is changing the world. It's changing what's possible in transportation, in health, in manufacturing, in ad placement. Basically everything where we have big data and we have hard problems, we're starting as a community to build these machine learning and artificial intelligence systems. Now, things that will move the needle in the future, I think, of course, better computers and better algorithms. That's a given. More data, more investment. We're investing tremendously in this. This is kind of the space race. We're all pushing towards these better artificial intelligence systems across the board. What will essentially, one of the things that I think will move the needle is understanding physics. So image classification, if you remember, like the facial recognition, it got better when it understood the physics that faces are not 2D, but they live on a three-dimensional skeleton. They live on a skull, okay? So that's an example of physics. What I'm going to call physics are the rules of the system. And so humans and biological systems are masters of understanding abstractly and in a hierarchical, fuzzy way the rules of the system, and using that to improve our learning rates and to assimilate new data more rapidly. And so I think that's going to be a transformative piece of this kind of developing machine learning and AI, is how do we bake in physics that we know? How do we teach the computer F equals ma, and there's conservation of mass and energy and momentum, so that we can get faster learning rates with less data? How do we extract unknown physics from these systems? If I just showed a machine learning algorithm a video of the night sky for weeks and weeks, can it learn the planetary orbits? Can it learn that there are stars and planets and that they're different? Can it learn F equals ma? Can it do what Newton did? I mean, we're not there yet. We're not even close. Okay, but extracting those symmetries and conservation laws and unknown physics from data, that's something I'm personally very excited about. It's relevant for self-driving cars. It's relevant for robots walking. I think it's relevant for image classification, because what is an image but a measurement of photons interacting with the physical world? Okay, so I think that's going to move the needle, as much as volumes of data and better algorithms and better computers. Okay, I hope you're excited. It's going to be an interesting world. You should watch this again in 5 years and laugh at what I said was going to be hard and how easy it is. Okay, thank you.